Hi, this is Yan Tian. Today, I will talk about our work, Contrastively Learning Visual Attention as Affordance Skills from Demonstrations for Robotic Grasping. This is a joint work with my fantastic collaborators, Sedant and Lin. Affordance describes the correlations among object, action, and effect. For grasping affordance, it's more about where and how to grasp. A grasp affordance is essentially a control configurations for external motion planner. The control configurations represent what could be applicable graphs for a specific region on an object. Now let's say we have 3 marks. Because of the different geometric features of different parts of the mark, for example, the handle, we need to lift the mark up by finding different possible grasps, like this. One way to learn grasp affordance is to learn clusters from grasping configurations like approaching orientations or grasp pre-shapes. And if such data come from human demonstrations, then we are going to the direction of learning affordance from demonstrations. Such works usually require an external motion planner that can take the affordance prediction as an input to perform a grasp. The main benefit is that we don't need to have the expensive procedure of collecting affordance labels. However, such work still decouples the learning of the policy and the learning of affordance. In our work, we want to know if we can combine the learning of the affordance and the policy together in an end-to-end framework. And by doing this, we could have the learning of affordance and policy benefit from each other. The objective of our work is that we want the robot to imitate not only the trajectory, but also the affordance tacit knowledge of the human teacher. So what does affordance tacit knowledge mean? So for example, by seeing this mark, the human may feel that the mark is graspable from its handle. And for this mark, the human thinks that it's graspable from its body. So the human will focus on the handle for this mark and the body for this mark. This is a tacit knowledge, and we call it an affordance cue in our work. Does affordance cue look like a visual attention? Yes. So there are some insights from cognitive psychology. For example, there is a close association between affordance and attention. They found that humans tend to focus on object parts that the human is going to manipulate to accomplish a task. So in our work, we use visual attention to model affordance cues. The reason that we can do this is mostly because we don't have an external motion planner as our actor. Instead, we use a neural network to represent a policy. The policy is a part of the whole neural network. And we can learn the policy to learn to adapt to the visual attention. Now, please let me explain at a high level how our system works. We have an environment like this, and we have a mark that is in a specific geometric shape. And we may have a different mark in a different episode. Now, human teaches a robot by grasping this mark from the handle and this smaller mark by body. The robot needs to self-explain what makes the two demonstrations different. We want the robot to discover that it is a handle for this mark and the body for this mark. That makes the two demonstrations different. So the robot needs to compare between the two demonstrations. And then robot could convert an observation advanced step to an affordance queue, and the policy model will take the affordance queue as a guidance to predict an action. So before we said that we want the robot to compare between the differences between two trajectories. So our core idea is to use contrastive learning framework for affordance discovery. Contrastive learning is a framework that can learn features by comparing between similar or different data points. So let's say we have a human to record the different demonstrations that can be classified into these three categories. By learning from such data, the contrastive learning should output the features that can be easily separatable in such an embedding space. And the features are separated in correspondence to the three categories. Contrastive learning typically requires three inputs. We sample one trajectory from one category, and we call such trajectory as an anchor trajectory. Then we sample another trajectory from the same category. We call it a positive sample. And then we sample the third trajectory from a different category. We call it a negative sample. And we have encoded to convert the three trajectories into three features. And then we could use the triplet loss, which is a popular contrastive learning loss function, to learn contrastive features. The triplet loss works by pulling together the features that come from the same category of trajectories and push away the features of the trajectories that come from different categories. However, you may find a challenge if you directly apply triplet loss to our problem. Now let's assume that we apply the triplet loss to a human demonstration. So a straightforward way is that we convert the observation at each step to an embedding. We call it the observation embedding, ZOA. Because the observation embedding comes from each step. It may condition on noisy contact factors like initial states and obstacles. As a result, ZOA may not be affordance relevant enough. So we introduce a new type of embedding we call it interaction embeddings. Remember, the affordance is used to describe the correlation among object, action, and effect. This is essentially an interaction. So inspired by this, we extract the steps between M and N, such that the gripper interacts or finishes with an object. So we call such segment as an interaction segment, which leads to an embedding called affordance embedding. And now we have two types of embeddings. One is affordance embedding, and the other is observation embedding. Now the question is, how can we couple their learning together? Or even more specifically, can we use the learning of affordance embeddings to guide the learning of observation embeddings? And this graphic model could describe what we want to do by using the affordance embedding to guide the learning of observation embedding. And we propose a couple of triple laws to do this. A couple of triple laws should make the observation embedding more affordance relevant by taking the guidance from the affordance embedding. And this is the equation or loss function of the couple of triple laws. It has two parts. The first part is essentially learning contrastive features from affordance embeddings. It's more or less like a traditional triple loss. And the second part is to use the affordance embedding to guide the learning of the observation embedding from the positive trajectory or negative trajectory. Now, let's put everything together. We have such framework. We have an input of the observation at one step. We also have the input of an interaction segment that is extracted from a trajectory, demonstration trajectory. And an attention model converts the observation to an affordance queue. And the encoder converts the affordance queue to an observation embedding. And we have an LSTM encoder to encode the interaction segment to an affordance embedding. The policy model takes the guidance from the affordance queue and the observation embedding to a predicted action. Now we have two optimization functions to train from the three outputs. The coupler triple loss takes the observation embedding and the affordance embedding. And because we have human demonstrations, we also have ground truth actions per step. So we can optimize the action prediction by using a behavior cloning loss. It's like the traditional behavior cloning loss by minimizing the distance between the predicted action and the ground truth action. Then we sum them together to get a final loss. And by minimizing the final loss, we can simultaneously learn affordance queues and the grasping policy. In our evaluation, we have a Franca Panda arm in a paraboloid simulator. In each episode, we randomly sample a mark. The mark could have a specific geometric feature and maybe even okay for grasping from multiple categories. Our video shows that, so in the left video, we show that the affordance queue is constant on the body part. Then the robot performs a body grasp. In this video, on the left, we show that the affordance queue shifts from both body and handle to just the handle. Then the robot performs a grasp on the handle. So this really matches the insights from cognitive psychology about the association between affordance queue and attention. We also did the evaluation in terms of grasping success rate. We show that our model with coupler triple loss performs the best. Now here are some takeaways. We essentially continue the direction of learning affordance from demonstrations due to the benefit that we can avoid the expensive procedure of collecting affordance labels. However, we go one step forward by initializing the direction of integrating the learning of affordance queues and the learning of policy in an end-to-end deep learning framework. And we further propose a couple of triple loss to allow robot not only imitate human at the trajectory level, but also at the mental level, which means robot imitate how human, what is human's tacit knowledge of affordance biases. You are very welcome to visit our project website. Thank you for listening to my talk.